Now let's talk about why SVD gives the best low-rank approximation. More specifically, we assume that the input matrix A is decomposed into three matrices, U, sigma, and V. And then we only keep the first k singular values in sigma and set the others to 0. And this is equivalent to keeping only the first k columns of U and keeping the first k rows of V transpose. And we call this matrix B. And we claim that B is the best approximation of A with a lower rank. Formally, we have the following theorem saying that if let A equal to U sigma V transpose and B equals to US V transpose, where the S is actually the diagonal R by R matrix, where we only keep the first k singular values in sigma and set all the others to 0. And then we have that B is the best rank k approximation to A. So what do we mean by best here? Remember that when we talk about best, we're actually meaning that we have the minimal reconstruction error in terms of Frobenius norm. So basically, we're saying that B is a solution to the following optimization problem where we're trying to minimize the Frobenius norm of A minus B, where the rank of B equals to K. And note that the SVD is actually equivalent to spectral decomposition of the matrix. And specifically, SVD can be seen as the sum of outer products. For example, the matrix A can be seen as the sum of several terms, and the first term is simply sigma 1 times U1 times V1, and the second term will be sigma 2 times U2 times V2. And remember that all these sigma, which are the singular values, they are already sorted. So basically, sigma 1 is equal to or larger than sigma 2 and equal to or larger than sigma 3, etc., etc. And also remember that both U and V, basically the left and right single matrix, they are column orthonormal, meaning that we can formally actually prove that the inner product of UI and VI is equal to 1. So with these observations, we can see why is setting smaller sigma I to 0 is the right thing to do. This is because the vectors UI and VI are unit length. So basically, the sigma I is the only thing that scales them. So the only thing that decides how large this term is just the sigma here. So basically, zeroing only the small sigma I would introduces less error. Another question is how many sigma s to keep? And usually a rule of thumb is to keep 80% to 90% of the energy, where the energy is defined as the sum of the square of the singular values. In terms of complexity, to compute SVD, we would need O n m square or O n square m, whichever is smaller. And this is for an input matrix of size n by n. But it will need less work if we just want the singular values, or if we just want the first k singular vectors, or if the matrix is sparse. And also nowadays, in terms of implementations, this SVD algorithm is already implemented in a lot of linear algebra packages, such as LinPack, MATLAB, SFAS, Mathematica. And to summarize, the conclusions so far for SVD is that for any real input matrix A, we can have a unique singular value decomposition. where the U is usually interpreted as the user to concept similarity, and the V can be interpreted as the movie to concept similarities. And the sigma indicates the strength of each concept. And to perform dimensionality reduction, we can just keep the few largest singular values. And usually a rule of thumb is to keep the number of largest singular values so that we can keep about 80% to 90% of the energy. And last but not least, what SVD does is essentially just to pick up and capture the linear correlations between the input space and the concept space.